In this video, we're going to do example 4.1.2, where we are asked to find and classify the critical points of f of xy is x cubed plus y cubed minus 3xy. To find the critical points, we need to examine places where the gradient of f equals 0 and the gradient of f does not exist. Now this is a polynomial. Well, this isn't a polynomial. F is a polynomial. And so there will be none. No places where the gradient does not exist. Now, where does the gradient equal the 0 vector? Let's calculate the two partials. So f sub x of xy is 3x squared minus 3y. And f sub y of xy is 3y squared minus 3x. We want both of these to be 0, so let's let 3x squared minus 3y equal 0 and 3y squared minus 3x equal 0 at the same time. We get the following, therefore, that y is equal to x squared, and if I take that and plug it into the second equation, right, this, both partials being 0 at once, gives us a system of equations. So I'm solving by isolating one variable and doing substitution, just like you would in any system of equations. This is obviously nonlinear, we have squares, but our method for solving is exactly the same. That means I'll have 3, I'll factor out the 3. Y squared is going to become x squared squared minus x is equal to 0, or 3x to the fourth minus x is 0, which we can factor and get 3x times x cubed minus 1 is equal to 0. So there are two possibilities here, either x is equal to 0 or x is equal to 1. If x is equal to 0, y is x squared, so we have the point 0, 0. And if x is equal to 1, y is 1 squared, y is equal to 1. So we have two critical points. We have the point 0, 0 and the point 1, 1 are the two critical points. We need to classify these, which means that we need to look at the Hessian determinant, which means that we need the second order partials. So let's calculate those. F sub xx, which means I'm taking the derivative of f sub x with respect to x, I will get 6x. F sub yy, so take the derivative of f sub y with respect to y, I will get 6y. And f sub xy, which is going to be equal to f sub yx, because these functions are continuous. That means I'm taking the derivative of f sub x, for instance, with respect to y. So if I take the derivative here with respect to y, this term disappears and I get minus 3. Let's just double check in the other one, f sub y. If I take the derivative with respect to x, this term disappears and I do get minus 3. So the Hessian determinant d of xy at any point xy is the determinant of 6x minus 3, and 6y, which is 36xy minus minus minus, so minus 9. We want to examine the point 0, 0. So d of 0, 0 is 36 times 0 minus 9 is minus 9, which is negative. And if the Hessian determinant is negative, we have a saddle point. Looking at the point 1, 1, d of 1, 1 is 36 times 1 times 1, so 36 minus 9 is 27, which is greater than 0. If the determinant is greater than 0, we need to examine the sign of f sub xx. F sub xx at 1, 1 is 6, which is also greater than 0. If both of them are greater than 0, then the point 1, 1 is a local minimum.